In recent advancements in multimodal AI and machine learning, several significant papers have been published, each contributing to the field in unique ways. 1. Law of Vision Representation in MLLMs. This paper introduces a framework for optimizing vision representation in multimodal large language models (MLLMs). By focusing on cross-modal alignment and vision-language correspondence, the authors present a method that significantly reduces computational costs while maintaining high performance. 2. CogVolm-2 Visual Language Models for Image and Video Understanding. Building on previous models, CogVolm-2 enhances the integration of visual and textual data, especially in high-resolution image and video tasks. The model introduces advanced techniques for temporal grounding in videos and achieves state-of-the-art results across several benchmarks. 3. Wave Tokenizer, an efficient acoustic discrete codec tokenizer for audio language modeling. This paper presents Wave Tokenizer, a new approach to tokenizing acoustic data for language models. It enhances efficiency in encoding audio information, providing better performance in tasks involving spoken language processing. 4. Reconx reconstruct any scene from sparse views with video diffusion model. Reconx introduces a novel method for scene reconstruction using sparse video inputs. The model utilizes a diffusion approach to improve the accuracy and quality of reconstructions, making it useful in scenarios with limited visual data. 5. SAM 2. Segment any 3D as videos in zero-shot and promptable manners. SAM 2. Offers an innovative solution for 3D segmentation in video data, providing zero-shot and prompt-based segmentation capabilities that enhance versatility in various 3D processing applications. 6. CSGO Content Style Composition and Text-to-Image Generation. This paper explores new methodologies for better aligning content and style in text-to-image generation, focusing on achieving a closer match between the generated images and the textual descriptions. 7. Physics of Language Models Part 2.2. How to learn from mistakes on grade school math problems. The study delves into methods for improving language models' ability to learn from mistakes, particularly in solving elementary math problems, enhancing their educational capabilities. 8. 3D reconstruction with spatial memory. This work presents a novel technique for 3D reconstruction using spatial memory, allowing for more accurate reconstructions from limited data inputs, particularly in challenging environments. 9. Styler Mix interpretable authorship obfuscation via distillation and perturbation of style elements. StyleMix introduces a method for obfuscating authorship in text by manipulating stylistic elements while preserving the content's meaning, making it difficult to trace back to the original author. 10. Scaling up diffusion and flow-based XGBoost models. The paper discusses scaling up diffusion models and integrating them with XGBoost, improving the ability to handle large datasets more efficiently. 11. Metaflow matching integrating vector fields on the Wasserstein manifold. This research introduces a complex mathematical approach for integrating vector fields on the Wasserstein manifold, with significant implications for improving flow matching in various machine learning applications. These papers collectively push the boundaries of how models process, integrate, and understand multimodal data, offering advancements in efficiency, performance, and application versatility. The paper titled Law of Vision Representation in MLLMs delves into the intricate relationship between visual representation and language processing within multimodal large language models (MLLMs). This relationship is crucial for tasks that require the integration of visual and textual data, such as image captioning, visual question answering, and more complex multimodal interactions. Overview of vision representation in MLLMs. To understand the technical details, we first need to recognize that MLLMs combine visual and textual data streams to produce cohesive outputs. Traditionally, these models require separate components of vision encoder to process images and a language model to handle text. The challenge lies in how these two components communicate and align with each other. Vision encoders and language models. Vision encoders, these are neural networks, often convolutional neural networks (CNNs) or vision transformers (VITs), that convert raw image data into a form that can be interpreted by the language model. The output of a vision encoder is a set of feature maps or embeddings that represent different aspects of the visual input. Language models these are based on architectures like transformer models, which process sequences of tokens, words, and generate context-aware embeddings that capture the meaning and relationships between those tokens. The core task in LMs is to align these visual and textual representations effectively so that the model can generate meaningful outputs that reflect both modalities. Key concepts introduced in the paper. Cross-modal alignment. This refers to the process of ensuring that the representations produced by the vision encoder are compatible with those produced by the language model. Effective alignment means that corresponding concepts in both modalities, e.g., an object and an image, and its textual description are represented similarly within the model's internal space. Correspondence in vision representation. This concept deals with how well the visual features extracted by the encoder correspond to the elements that the language model needs to process. It's not enough for the vision encoder to produce detailed feature maps. These features must be structured in a way that the language model can utilize effectively. AC score alignment and correspondence score. The authors introduce a metric called the AC score to quantify the effectiveness of the cross-modal alignment and the quality of the vision representations. The AC score is calculated by evaluating the alignment between the visual and textual representations across different layers of the model. A higher AC score indicates better alignment and correspondence, which should correlate with improved performance on downstream tasks. Technical methodology. Experiment design. The authors conduct a series of experiments to test the effectiveness of different vision representation strategies. These experiments involve varying the architecture and configuration of the vision encoder, the type of visual features extracted, and how these features are integrated with the language model. They use 13 different vision representation settings and evaluate their impact on 8 benchmarks, including standard tasks like image captioning and visual question answering. Each configuration is assessed using the EC score, which provides a quantitative measure of how well the vision and language components are aligned. Layer-wise alignment analysis. One of the innovative aspects of this research is the detailed layer-wise analysis of alignment within the MLLM. The authors examine how the alignment between vision and language representations evolves across different layers of the model. Typically, lower layers of the model handle more basic features like edges or textures in images and simple syntax in text, while higher layers capture more abstract concepts like object categories in images and semantic meanings in text. By analyzing the AC score at each layer, the researchers can identify where the alignment is strongest and weakest, allowing them to optimize the vision representation at those critical points. Reduction in computational costs. A significant finding of the study is that by focusing on optimizing the vision representation based on the AC score, it is possible to achieve near optimal performance without needing to retrain the entire language model. This is a major breakthrough because retraining large language models is computationally expensive and time-consuming. The authors report a 99.7% reduction in computational cost, which is achieved by optimizing only the vision component while maintaining the pre-trained language model unchanged. Detailed results and implications. The results of the experiment show a clear linear relationship between the EC score and the performance of the MLLM across various tasks. This finding validates the author's hypothesis that better aligned vision and language representations lead to improved model performance. The paper also discusses the broader implications of these findings for the development of more efficient and scalable MLL. By focusing on optimizing vision representation and alignment, developers can create models that are both more powerful and more efficient, with lower computational requirements and faster training times. Conclusion. In summary, the law of vision representation in LMs provides a comprehensive framework for understanding and optimizing the interaction between visual and textual data in multimodal models. The introduction of the AC score as a metric for alignment and correspondence is a key innovation that allows for targeted improvements in model performance without the need for extensive retraining. This work represents a significant advancement in the field of multimodal AI, offering practical insights and methodologies that can be applied to a wide range of applications. The paper CogVom2 Visual Language Models for Image and Video Understanding represents a significant advancement in the field of visual language models VLMs, building upon the foundations laid by earlier models such as VisualGO and the original CogVom. The CogVom2 family introduces several key innovations aimed at improving the integration and performance of visual and textual data processing for both images and videos. Overview of CogVom2. CogVom2 is designed to enhance vision-language fusion, providing a more sophisticated framework for understanding both images and videos within a multimodal context. The family includes several models such as CogVom2 for image understanding, CogVom2 Video for video understanding, and GLM4V, which expands the modalities and applications of the model. Core components. 1. Visual Expert Architecture. CogVom2 retains the Visual Expert Architecture from its predecessor, but with significant improvements. This architecture is key to how the model processes visual data before integrating it with the language model. The Visual Expert module is embedded within the attention and feed-forward layers of the transformer architecture, ensuring deep fusion of visual and textual information. This allows the model to handle high-resolution images up to 1344 x 1344 pixels and supports complex visual understanding tasks. 2. Multi-frame input and temporal grounding for video understanding. HuggingFace video introduces the capability to process multi-frame inputs with associated timestamps. This enables the model to understand temporal dynamics in videos, an essential feature for tasks like video question answering or activity recognition. The model also incorporates a novel method for automated temporal grounding, which aligns specific frames or sequences in a video with relevant textual information, enhancing the model's ability to accurately interpret and respond to queries about video content. Training and post-training enhancements. HuggingFace 2 incorporates advanced training recipes that optimize both the pre-training and post-training phases. These improvements include better data augmentation techniques, refined loss functions, and more efficient use of computational resources during training. The post-training phase benefits from fine-tuning strategies that further align the visual and language components, ensuring the model performs optimally across a variety of tasks. Performance and benchmarks. HuggingFace 2 achieves state-of-the-art results across multiple benchmarks, including MMBench, MMVet, TextDQA, MDBench, and BCGBench. These benchmarks cover a range of tasks, from basic image and video understanding to complex multimodal reasoning. The model's performance on these tasks demonstrates its superior ability to handle both visual and textual data, making it one of the leading models in the field. 1. Image understanding. HuggingFace 2 excels in image-based tasks, significantly outperforming previous versions and even competing with some non-open source models. The improvements are particularly noticeable in tasks that require high-resolution image processing and complex visual reasoning. 2. Video understanding. HuggingFace 2 video sets new standards for video understanding tasks, such as video question answering. By effectively handling multi-frame inputs and integrating temporal information, the model outperforms existing benchmarks, showcasing its ability to understand and process dynamic visual data. Technical advancements and contributions. The HuggingFace 2 family brings several technical advancements to the table. Higher resolution support. The model's architecture supports higher input resolutions, allowing for more detailed image processing. Temporal grounding, a new approach to align video frames with textual descriptions, crucial for tasks that involve understanding time-based visual data. In-depth explanation of temporal grounding in HuggingFace 2. Temporal grounding is a critical concept in video understanding tasks within multimodal models like HuggingFace 2. It refers to the process of aligning specific moments or sequences in a video with corresponding textual descriptions or queries. This capability is essential for tasks where the model needs to understand not just what happens in a video, but also when it happens. Key concepts in temporal grounding. 1. Temporal context. Videos are fundamentally different from images because they involve a time dimension. Understanding a video requires the model to consider the sequence of frames and how actions or events unfold over time. Temporal grounding ensures that the model can accurately associate particular frames or sequences of frames with specific textual information, such as questions or descriptions. 2. Temporal anchors. In the context of video question answering, videoca, or video captioning, temporal anchors are specific moments or intervals in the video that are relevant to the query or task. For example, in a sports video, a temporal anchor might be the exact moment when a goal is scored. Temporal grounding involves detecting these anchors and linking them to the appropriate textual descriptions. 3. Multi-frame input with timestamps. HuggingFace 2 video integrates multi-frame inputs with timestamps, which allows the model to process sequences of frames along with their corresponding time information. This is crucial for temporal grounding because it enables the model to keep track of when specific actions occur and how they relate to one another over time. How temporal grounding works in HuggingFace 2. Automated temporal grounding data construction. One of the innovations in HuggingFace 2 video is the automated construction of temporal grounding data. This involves creating a data set where specific frames or sequences within a video are labeled with the relevant textual information. For instance, a segment of a video where a person is speaking might be labeled with the corresponding dialogue or a query about what is being said. Temporal attention mechanisms. HuggingFace 2 video likely employs temporal attention mechanisms, which are extensions of the attention mechanisms used in standard transformers. These mechanisms allow the model to focus on relevant time segments within the video when processing a query. Temporal attention enables the model to weigh different frames differently depending on their relevance to the task at hand. Frame-to-text alignment. For effective temporal grounding, CogVom2 video aligns the visual features from specific frames with the corresponding text. This alignment is crucial for tasks like video captioning or answering time-specific questions. The model must be able to match the visual content from a particular moment in the video with the text that describes or queries it. Temporal consistency, ensuring that the model maintains consistency in understanding the sequence of events, is another critical aspect of temporal grounding. Temporal consistency means that the model's interpretation of the video remains coherent over time, accurately reflecting the sequence of events without being confused by irrelevant or out-of-order frames. Application in video question answering videoca. In videoca, temporal grounding allows the model to correctly identify the moment in the video that answers a specific question. For example, if asked, "When did the cat jump?" the model needs to locate the exact frame or sequence of frames showing the cat jumping and provide the correct timestamp or description based on that action. Challenges and innovations. Temporal grounding is inherently challenging due to the complexity of video data. Unlike static images, videos involve dynamic scenes, varying frame rates, and potential ambiguities in when certain actions occur. CogVom2 video addresses these challenges by integrating sophisticated temporal processing capabilities that allow the model to handle complex, time-based queries with high accuracy. In summary, temporal grounding in CogVom2 video is about accurately linking the temporal aspects of video data such as specific frames or sequences of actions with corresponding textual information. This involves the use of temporal attention mechanisms, multi-frame inputs with timestamps, and automated data construction techniques, all of which contribute to the model's ability to perform complex video understanding tasks effectively. Optimized training recipes enhance training methodologies that improve both efficiency and performance, making the model more practical for large-scale applications. Optimized training in CogVom2. The optimized training process in CogVom2 is a sophisticated approach designed to enhance the performance of the model while making efficient use of computational resources. This process is divided into two main stages: pre-training and post-training, each optimized with specific techniques to improve the model's ability to integrate visual and textual data effectively. Pre-training enhancements. 1. Advanced data augmentation. In the pre-training phase, CogVom2 utilizes advanced data augmentation techniques to diversify the training data and improve the model's robustness. Data augmentation involves transforming the training data in various ways, such as rotating, flipping, or cropping images so that the model learns to recognize and process images under different conditions. This is particularly important for tasks requiring high-resolution image processing, where slight variations in the input data can significantly impact performance. 2. Optimized loss functions. CogVom2 introduces optimized loss functions tailored to multimodal learning. These loss functions are crucial for guiding the model to learn meaningful representations from both visual and textual data. The loss functions used in CogVom2 likely include components that penalize misalignment between image and text representations, ensuring that the model learns to correctly associate visual features with their corresponding textual descriptions. 3. Efficient use of computational resources. The model employs strategies to reduce the computational load during pre-training, such as mixed precision training, which balances the trade-off between speed and accuracy. Mixed precision training uses lower precision, e.g., 16-bit floating point for certain calculations, which reduces memory usage and speeds up the training process without significantly compromising model performance. Post-training enhancements. 1. Fine-tuning strategies. After the initial pre-training, CogVom2 undergoes a fine-tuning phase where the model is further adjusted to optimize performance on specific tasks. This fine-tuning process involves adjusting the model's parameters based on smaller, task-specific datasets. In the context of video understanding, fine-tuning might involve focusing on improving the model's temporal grounding capabilities or enhancing its ability to process high-resolution frames. 2. Layer-wise learning rate adjustment. To further refine the model during fine-tuning, CogVom2 may use layer-wise learning rate adjustments. This technique involves setting different learning rates for different layers of the model, with lower learning rates for layers closer to the input, which are more general, and higher rates for layers closer to the output, which are more task-specific. This allows for more precise adjustments, ensuring that the model becomes more specialized in handling the specific tasks it will perform. 3. Knowledge distillation. In some cases, knowledge distillation is used during post-training. This technique involves training a smaller, more efficient model the student to replicate the behavior of a larger, more complex model the teacher. The student model is then fine-tuned further, leveraging the distilled knowledge to achieve high performance with reduced computational requirements. HuggingFace 2 represents a significant evolution in the development of visual language models, particularly in how it processes and integrates multimodal data for both image and video understanding. The model's ability to perform temporal grounding enables it to handle complex video-based tasks with precision, marking a substantial improvement over previous models. Moreover, the optimized training strategies employed, ranging from advanced data augmentation and tailored loss functions to efficient fine-tuning and knowledge distillation, ensure that HuggingFace 2 is not only powerful but also computationally efficient. This combination of innovative features and optimized training makes HuggingFace 2 a leading model in the field, pushing the boundaries of what is possible in visual and textual data integration. The open sourcing of HuggingFace 2 further contributes to the broader AI community, enabling continued research and development in multimodal AI. The paper titled WAV Tokenizer, an efficient acoustic discrete codec tokenizer for audio-language modeling presents a groundbreaking approach to audio tokenization, specifically designed for use in audio-language models. The primary goal of WAV Tokenizer is to efficiently compress high-dimensional audio signals, such as speech and music, into lower-dimensional discrete tokens, while maintaining high reconstruction quality. Background and motivation. In audio processing, language models often require the conversion of complex audio signals into a form that can be efficiently processed. Traditional methods involve high-dimensional continuous representations that are computationally expensive and difficult to integrate with language models. To address these challenges, the authors introduced WAV Tokenizer, which compresses these signals into discrete tokens, significantly reducing dimensionality without sacrificing quality. Core concepts. Extreme compression WAV Tokenizer achieves remarkable compression by reducing the layers of quantizers and the temporal dimension of the audio signal. For instance, a 1-second audio clip at a 24 kHz sampling rate is represented using just a single quantizer with 40 to 75 tokens. This extreme compression allows for efficient storage and processing of audio data, making it ideal for large-scale audio language models. Improved reconstruction quality. Despite the drastic reduction in the number of tokens, WAV Tokenizer maintains state-of-the-art reconstruction quality. This is achieved through a combination of techniques, including the design of a broader vector quantization VQ space, extended contextual windows, and enhanced attention networks. These improvements ensure that the compressed tokens still contain rich semantic information, essential for tasks like speech recognition and music analysis. Advanced model architecture. The model's architecture includes a multi-scale discriminator and an inverse Fourier transform structure, which together enhance the model's ability to reconstruct high-quality audio from the discrete tokens. The multi-scale discriminator helps the model differentiate between various levels of detail in the audio signal, ensuring that even subtle audio features are preserved during compression and reconstruction. Methodology and experiments. The authors conducted extensive experiments across various domains, including speech, general audio, and music, to test the performance of WAV Tokenizer. They evaluated the model using both objective metrics such as token utilization and compression efficiency, and subjective metrics like utmost scores, which measure perceived audio quality. The results consistently showed that WAV Tokenizer outperforms existing state-of-the-art models in terms of both efficiency and quality. Ablation studies. To validate the contributions of each component of WAV Tokenizer, the authors performed comprehensive ablation studies. These studies involve systematically removing or altering components of the model, such as the VQ space or the attention mechanisms, to observe their impact on performance. The results confirmed that each element of WAV Tokenizer plays a crucial role in achieving its high performance, particularly in maintaining semantic richness and high-quality audio reconstruction. Conclusion. WAV Tokenizer represents a significant advancement in the field of audio-language modeling by introducing an efficient and high-quality method for compressing audio signals into discrete tokens. Its ability to perform extreme compression while preserving essential audio features makes it a powerful tool for various applications, including speech recognition, music processing, and beyond. The open-source nature of WAV Tokenizer, along with the provided code and pre-trained models, allows for further exploration and application by the broader research community. Improved reconstruction quality. Reconstruction quality in audio models refers to how accurately the model can reproduce the original audio signal after it has been compressed and then decoded. In the case of WAV tokenizer, several advanced techniques are employed to ensure that the quality of the reconstructed audio remains high, even after significant compression. 1. Broader vector quantization VQ space. Vector quantization is a technique used to reduce the dimensionality of continuous signals by mapping them into a discrete space. In WAV tokenizer, the VQ space is designed to be broader, meaning it includes a more extensive range of possible quantized values. This allows for more precise representation of the original audio signal within the compressed format. A broader VQ space helps preserve the fine details of the audio, which are crucial for maintaining high perceptual quality in the reconstructed signal. 2. Extended contextual windows. Contextual windows refer to the range of time steps that the model considers when processing each frame of audio. By extending these windows, WAV tokenizer can capture more temporal context, which is essential for accurately modeling the dependencies in audio signals that occur over time. This extension is particularly important in complex audio signals like music, where harmonics and rhythms need to be preserved across longer time spans. 3. Improved attention networks. Attention mechanisms are a key component in modern neural networks, particularly in transformer architectures. In WAV tokenizer, the attention networks are optimized to focus on relevant parts of the audio signal more effectively. This means that the model can better distinguish between important and less important features of the signal, leading to a more accurate reconstruction. The attention mechanism dynamically weighs the importance of different parts of the input when generating the output, ensuring that critical features are given more importance during the reconstruction phase. Advanced model architecture. WAV tokenizer's architecture includes several innovative components that work together to enhance its ability to compress and reconstruct audio signals efficiently. 1. Multi-scale discriminator. A discriminator is typically used in generative adversarial network scans to differentiate between real and generated data. In WAV tokenizer, a multi-scale discriminator operates across different resolutions or scales of the audio signal. This component ensures that the model can accurately capture both the fine details like high-frequency components and the broader structures like rhythm and melody in music. The multi-scale approach helps the model maintain high fidelity in the reconstructed audio by ensuring that both micro and macro aspects of the audio are well represented. 2. Inverse Fourier transform structure. The inverse Fourier transform IFT is used to convert frequency domain data back into the time domain, which is essential for reconstructing audio signals. WAV tokenizer integrates an IFT structure into its architecture to facilitate this process. By doing so, the model ensures that the compressed tokens, which may represent frequency domain features, can be accurately transformed back into high-quality time domain audio signals. The IFT helps retain the phase information, which is critical for the naturalness and clarity of the audio. Ablation studies. Ablation studies are a crucial aspect of model validation, where different components or features of the model are systematically removed or altered to understand their impact on the overall performance. 1. Component removal. In WAV tokenizer, the authors performed ablation studies by selectively removing key components such as the VQ space, attention mechanisms, or the multi-scale discriminator. By evaluating the model's performance after each removal, they could determine the contribution of each component to the model's success. For instance, removing the extended contextual windows might lead to a noticeable drop in reconstruction quality, demonstrating its importance. 2. Impact on metrics. The ablation studies involve measuring changes in various performance metrics, including objective measures like token utilization, how efficiently the tokens are used, and subjective measures like utmost scores, a metric for perceived audio quality. These studies provided empirical evidence for the necessity of each module in the architecture. For example, the studies might reveal that the broader VQ space significantly improves utmost scores, indicating better subjective audio quality. 3. Validation across domains. The studies also tested the model across different domains such as speech, general audio, and music to ensure that the improvements are consistent and not domain-specific. This helps validate that WAV tokenizer's architecture is robust and generalizable across various types of audio data. Conclusion. WAV tokenizer represents a significant advancement in the field of audio tokenization, providing an efficient and high-quality method for compressing audio signals into discrete tokens. Its success is due to a combination of techniques aimed at improving reconstruction quality, such as the broader VQ space, extended contextual windows, and improved attention networks. The advanced architecture, including the multi-scale discriminator and inverse Fourier transform structure, plays a crucial role in maintaining high fidelity in the reconstructed audio. Finally, the comprehensive ablation studies underscore the importance of each component, demonstrating that WAV tokenizer's design is both innovative and essential for achieving state-of-the-art performance in audio language modeling. The paper Reconx Reconstruct Any Scene from Sparse Views with Video Diffusion Model introduces a novel approach to 3D scene reconstruction using sparse visual data. The challenge in reconstructing 3D scenes from sparse views, where only a few images of the scene are available, is that traditional methods often result in artifacts or distorted reconstructions due to the lack of sufficient visual information. Reconx addresses this issue by leveraging large pre-trained video diffusion models, which have a strong generative capability. The key innovation of Reconx is reframing the reconstruction task as a temporal generation problem. This approach uses the generative power of video diffusion models to generate additional views or frames that maintain a high degree of 3D consistency across different perspectives. To begin the reconstruction process, Reconx first creates a global point cloud from the limited input views. This point cloud acts as a rough 3D structure of the scene and is encoded into a contextual space, serving as the 3D condition for the subsequent steps. Next, the video diffusion model, guided by this 3D structure, synthesizes new video frames that preserve fine details and maintain consistent 3D geometry. These generated frames are crucial for filling in the gaps left by the sparse views and help in constructing a more complete and accurate 3D model. The final step involves a confidence-aware 3D Gaussian splatting optimization. This technique refines the reconstructed 3D scene by optimizing the consistency and accuracy of the point cloud using the synthesized video frames. Extensive experiments demonstrate that Reconx outperforms state-of-the-art methods, particularly in terms of reconstruction quality and the ability to generalize across different datasets. The model shows strong potential in applications where only a limited number of views are available, such as in certain remote sensing or surveillance scenarios. Point cloud as a rough 3D structure and encoding into contextual space. In the context of Reconx, the point cloud acts as a foundational representation of the 3D scene. A point cloud is essentially a collection of data points in a three-dimensional space, where each point represents a position on the surface of an object or scene. When dealing with sparse views, meaning only a few images of a scene are available, the initial challenge is to construct a rough 3D representation from these limited perspectives. Reconx approaches this by generating a global point cloud from the input images. The process typically involves estimating depth information from each available view, which is then used to project 2D points from the images into 3D space. However, with sparse data, this point cloud is often incomplete and lacks detail, especially in areas not captured by the input images. This rough point cloud serves as a preliminary structure that hints at the overall geometry of the scene, but it's not sufficient for accurate reconstruction by itself. To overcome this limitation, Reconx encodes the point cloud into a contextual space. Encoding here means transforming the 3D data into a more abstract representation that can be used by the model in subsequent steps. The encoding process captures the global geometric context of the scene by considering the spatial relationships between points in the cloud. This is crucial because it allows the model to understand not just where individual points are, but how they relate to the overall structure of the scene. This encoded representation serves as the 3D condition for the video diffusion model in the next step, essentially guiding the model on how the 3D structure should influence the generation of new frames. Video diffusion model guided by 3D structure. The video diffusion model is the core generative component of Reconx, responsible for synthesizing new video frames that are consistent with the 3D geometry of the scene. Diffusion models are a type of generative model that work by iteratively refining noise into a coherent image or sequence of images. In the context of Reconx, the video diffusion model uses the encoded 3D structure from the point cloud as a guide or condition during this generative process. This guidance ensures that the generated frames are not only visually plausible but also consistent with the underlying 3D geometry of the scene. The model achieves this by conditioning the generation of each frame on the global 3D context provided by the encoded point cloud. This means that as the model generates each frame, it takes into account the spatial relationships and geometry encoded in the 3D condition, ensuring that the resulting frames align correctly with the overall scene structure. The video diffusion model operates in a temporal generation framework, meaning it generates a sequence of frames over time, rather than individual frames in isolation. This temporal aspect is critical for maintaining 3D consistency across the generated frames. For example, as the model generates a sequence of frames representing a rotating object, it must ensure that the object's features move coherently from one frame to the next, respecting the object's 3D structure. The guidance from the 3D condition helps maintain this coherence, ensuring that the generated frames not only look good individually, but also fit together correctly to represent a consistent 3D scene when viewed in sequence. Importance of generated frames in filling gaps. The generated frames play a crucial role in filling the gaps left by the sparse input views. Sparse views mean that certain areas of the scene are not captured in the input images, leading to incomplete information in the initial point cloud. The video diffusion model, guided by the encoded 3D structure, generates new frames that effectively fill in these missing parts of the scene. These generated frames provide additional viewpoints that were not originally captured, allowing the model to create a more complete and accurate representation of the scene. By ensuring that these frames are consistent with the 3D geometry, the model can generate plausible content for the unseen areas, mitigating artifacts and distortions that typically occur in regions with insufficient data. This process is essential for achieving a high-quality reconstruction that accurately reflects the true appearance and structure of the scene. Confidence-aware 3D Gaussian splatting optimization. The final step in the Reconx pipeline is the confidence-aware 3D Gaussian splatting optimization. This is an advanced technique used to refine the reconstructed 3D scene based on the generated frames. Gaussian splatting is a method used to render 3D point clouds by representing each point as a Gaussian distribution rather than a single point. This approach allows for smoother and more continuous surfaces in the reconstructed scene, as the Gaussians can overlap and blend together, filling in gaps between points. In Reconx, this method is used to transform the rough point cloud into a more polished 3D model. The confidence-aware aspect refers to the model's ability to weigh different parts of the generated data, according to their reliability or confidence level. For example, areas of the point cloud that are well supported by multiple input views might be assigned higher confidence, while regions generated by the diffusion model and thus based more on inference might have lower confidence. The optimization process adjusts the influence of each point in the Gaussian splatting process based on these confidence levels, ensuring that the final 3D model emphasizes more reliable data and minimizes the impact of potentially less accurate generated content. This leads to a final reconstructed scene that is both accurate and visually coherent, with minimized artifacts and distortions. Summary. In summary, Reconx leverages a point cloud as an initial rough 3D structure and encodes it into a contextual space to guide a video diffusion model in generating consistent, detail-preserving video frames. These frames fill in the gaps left by sparse input views, contributing to a more complete and accurate 3D reconstruction. The final refinement is achieved through confidence-aware 3D Gaussian splatting optimization, which polishes the model by smoothing surfaces and weighing the reliability of different data points. This multi-step process enables Reconx to produce high-quality 3D reconstructions even from limited visual data, making it a powerful tool for various applications in computer vision and graphics. The paper titled CSGO Content Style Composition and Text-to-Image Generation presents a sophisticated framework for achieving high-quality image style transfer and syntheses using diffusion models. This work addresses a critical challenge in text-to-image generation, effectively combining the content of one image with the stylistic attributes of another, while ensuring that the resulting image remains coherent and true to the original content. Overview of CSGO. CSGO introduces an end-to-end training model that explicitly decouples content and style features through independent feature injection mechanisms. The model operates in three main modes. Image-driven style transfer. This mode focuses on transferring the style of one image onto the content of another. Text-driven stylized synthesis. Here, the model generates images based on text prompts while adhering to specific stylistic guidelines. Text editing-driven stylized synthesis. This involves editing an existing image using text prompts to adjust its style or content. Methodology. The core innovation of CSGO lies in its data construction pipeline, which generates and cleanses large-scale stylized image triplets. These triplets are essential for training the model to understand and separate content from style effectively. The model leverages a dataset called MAG-Style, containing 210,000 image triplets, specifically designed for research and development and style transfer. CSGO utilizes a control net and a decoupled cross-attention module to separately manage content and style extraction. Content information is injected into the model using control net, ensuring that the original semantics of the content are preserved. Style information is independently extracted and applied to the content using a decoupled cross-attention mechanism, allowing for precise control over the style while maintaining the integrity of the content. Results: extensive experiments have demonstrated the model's effectiveness in style control, outperforming existing methods in both qualitative and quantitative comparisons. CSGO has shown its ability to maintain the generative power of the original text-to-image models while enhancing their flexibility and control over style composition. This paper makes significant contributions to the field of text-to-image generation by introducing a robust and versatile model capable of high-quality style transfer and synthesis. The approach taken by CSGO is a promising step forward in achieving more controllable and realistic image generation outcomes in various applications. The CSGO model shares some conceptual similarities with variational autoencoders Vase and embeddings, but it operates differently in practice, particularly due to its use of diffusion models and its focus on explicit content-style decoupling. Similarities to Vase: latent space representation like Vase, CSGO likely operates within a latent space where content and style are encoded into distinct representations. In Vase, data is encoded into a latent space from which it can be sampled and decoded back into the original domain. This is somewhat analogous to how CSGO separates and manipulates content and style. Decoupling of features Vase often involve learning disentangled representations, where different dimensions of the latent space control different aspects of the data, e.g., one dimension might control the overall shape, another might control color. Similarly, CSGO explicitly decouples content and style features, although it does so through specific network architectures like ControlNet and cross-attention modules, rather than through the typical encoder-decoder structure of a VE. Similarities to embeddings: feature embedding. Both CSGO and typical embedding techniques involve representing features' content and style in the case of CSGO in a lower dimensional space that makes it easier to manipulate and combine these features. In embedding spaces, different vectors can represent different attributes like words in a sentence or objects in an image, and their relationships, e.g. similarities, differences are captured in the space. Transferability embeddings are often designed to be transferable between different tasks. CSGO's use of independent feature injection and its ability to handle multiple tasks, image-driven transfer, text-driven synthesis, etc. a similar kind of versatility. Key differences: diffusion models, unlike Vase, which use a probabilistic approach to generate new data from latent variables, CSGO uses diffusion models that iteratively refine an image by reversing a noise process. This makes the generation process in CSGO quite different from the typical generative process in a Vase. Explicit control mechanisms. While Vase and embeddings can allow for some degree of control over the generated content by manipulating the latent space or embedding vectors, CSGO provides explicit mechanisms for controlling style and content separately through its architecture. This allows for more precise and intentional modifications. In summary, while there are some conceptual overlaps between CSGO and Vase or embeddings, especially in the idea of representing and manipulating features in a structured space, CSGO's implementation is distinct. This is particularly due to its use of diffusion models and specific architectural choices designed for content-style decoupling and synthesis. The paper titled Physics of Language Models Part 2.2, How to Learn from Mistakes on Grade School Math Problems, focuses on improving the reasoning capabilities of language models by incorporating error correction data directly into the pre-training stage. The primary motivation behind this work is the observation that even the most advanced language models can still make mistakes in reasoning tasks, particularly when solving complex problems like grade school math. Overview: language models, particularly those used in reasoning tasks, have shown significant progress in handling complex problems. However, these models still occasionally produce incorrect results, especially in multi-step reasoning tasks such as solving math problems. Traditionally, when a language model makes a mistake, techniques like multi-round prompting are used to guide the model towards the correct answer by rephrasing the problem or asking follow-up questions. However, this approach can be inefficient as it generates unnecessary tokens and increases the time needed for inference. Key concepts and methodology. Error correction data. The central idea of this paper is to introduce a new type of pre-training data that includes both erroneous steps and their immediate corrections. Instead of training the model solely on error-free data, the authors propose incorporating examples where mistakes are made and then corrected, simulating a more realistic learning environment similar to how humans learn from their mistakes. This data is synthetically generated using a large set of elementary math problems, allowing the model to encounter a wide variety of errors and corrections. Autoregression and direct reasoning. The paper shows that by training on error correction data, language models can achieve higher reasoning accuracy directly through simple autoregression. This approach contrasts with traditional methods that rely on techniques like beam search or iterative refinement during inference. The error correction pre-training allows the model to better internalize the correct reasoning processes, reducing the need for complex prompting strategies during actual problem solving. Detailed experimentation. The authors conducted extensive experiments to understand the impact of various factors, such as the amount of error data, the necessity of masking erroneous tokens, and whether this approach could be deferred to the fine-tuning stage instead of being applied during pre-training. They also explored how this method differs from beam search, another common technique for improving model accuracy and reasoning tasks. In-depth analysis of key concepts. 1. Error correction data and pre-training. A. Definition and purpose. Error correction data refers to training examples that not only present correct solutions but also include intentional mistakes followed by their corrections. This dual-component approach mirrors real-world learning scenarios where learners make errors and subsequently learn from them. B. Implementation strategy. Synthetic generation. The authors employ a synthetic approach to generate error correction pairs. By algorithmically introducing controlled errors into solution steps of grade school math problems, they create a diverse dataset that simulates common mistakes. Types of errors can range from simple arithmetic mistakes to more complex reasoning flaws. The diversity ensures that the language model is exposed to a wide spectrum of potential errors, enhancing its ability to recognize and correct them. C. Benefits in pre-training. Enhanced robustness. By encountering and correcting errors during pre-training, the model develops a more nuanced understanding of problem-solving processes, making it less prone to similar mistakes during inference. Improved generalization. Exposure to error patterns allows the model to generalize better across different types of problems, as it learns to identify underlying structures that may lead to errors. 2. Autoregression and direct reasoning. A. Autoregression mechanism. Autoregression in language models involves predicting the next token in a sequence based on the preceding tokens. Traditionally, this approach focuses on generating coherent and contextually relevant text without explicit mechanisms to correct prior errors. B. Integration with error correction data. Direct reasoning enhancement. By incorporating error correction data, the autoregressive process is augmented to not only predict subsequent tokens, but also to recognize and rectify preceding mistakes within the same sequence. Seamless correction. This integration allows the model to internally adjust its reasoning trajectory without the need for external prompting or iterative refinement, streamlining the inference process. C. Comparative advantage. Efficiency. Unlike multi-round prompting, which requires multiple passes and increases computational overhead, the enhanced autoregressive approach achieves higher accuracy in a single pass. Scalability. The method scales more effectively for large-scale applications, as it minimizes the latency associated with iterative correction mechanisms. 3. Detailed experimentation and analysis. A. Parameter variations. The authors conducted experiments varying several parameters to assess the impact of error correction data on model performance. Amount of error data. Analyzing how the proportion of error correction pairs relative to error-free data affects reasoning accuracy. Masking erroneous tokens. Investigating whether obscuring the erroneous parts of the data during training influences the model's ability to learn corrections. Deferral to fine-tuning, exploring if introducing error correction data during the fine-tuning phase, as opposed to pre-training, yields similar benefits. B. Comparative techniques. Beam search differentiation. Beam search is a decoding strategy that explores multiple possible output sequences to find the most probable one. The authors differentiate their approach by emphasizing internal error correction over external search strategies. Control mechanisms. Unlike traditional models that rely on latent space manipulations for control, the proposed method employs explicit error correction pathways, providing more deterministic and interpretable control over the reasoning process. C. Metrics and evaluation. Reasoning accuracy. Primary metric focusing on the correctness of solutions to math problems. Inference efficiency, measuring the computational resources and time required to generate solutions, highlighting the efficiency gains from reduced need for multi-round prompting. Generalization capability, assessing the model's performance across varied problem types and complexities to ensure broad applicability. 4. Theoretical foundations and architectural innovations. A. Diffusion models vs. Variational autoencoders vs. Diffusion models. These models iteratively refine data by reversing a noise process, gradually transforming a noisy input into a coherent output. In the context of language models, this allows for step-by-step enhancement of reasoning processes. These utilize a probabilistic framework to encode data into a latent space and then decode it back, focusing on capturing the underlying distribution of the data. B. Architectural distinctions. Content style. Decoupling the proposed architecture separates content generation from stylistic elements, enabling more precise control over the reasoning and solution presentation. Independent feature injection. This mechanism allows the model to incorporate specific features or corrections without entangling them with the primary content generation pathways, enhancing modularity and flexibility. C. Implications for transferability. The architectural choices facilitate transfer learning, where the pre-trained model can be adapted to various reasoning tasks beyond grade school math. The separation of concerns within the model's architecture ensures that learned error correction capabilities are not tightly coupled to specific problem types, promoting broader applicability. 5. Practical applications and future directions. A. Beyond grade school math. While the study focuses on elementary math problems, the underlying methodology has potential applications in more complex domains such as advanced mathematics and physics, extending error correction mechanisms to higher-level problem solving, programming and code generation, applying similar techniques to identify and correct logical or syntactical errors in code, natural language understanding, enhancing models' ability to correct grammatical or semantic errors in text generation tasks. B. Integration with existing systems. The proposed approach can be integrated into existing language model frameworks to enhance their reliability and accuracy, especially in educational technologies, automated tutoring systems, and intelligent assistants that require precise reasoning capabilities. C. Future research directions. Adaptive error generation, developing more sophisticated methods for generating error correction data that better mimic human error patterns. Real-world data incorporation, incorporating error correction data derived from real-world interactions and mistakes to further enhance model robustness. Multilingual and cross-domain extensions, exploring the applicability of error correction pre-training across different languages and diverse problem domains. Conclusion. The results of the study are promising, showing that incorporating error correction data into the pre-training stage can significantly enhance the model's reasoning capabilities. This improvement is achieved without the need for multi-round prompting, making the inference process faster and more efficient. The findings suggest that this approach could be broadly applicable to other reasoning tasks beyond grade school math, potentially leading to more robust and reliable language models across various domains. In summary, Physics of Language Models Part 2.2 offers a novel approach to enhancing language models' ability to learn from mistakes, leading to improved accuracy and efficiency in reasoning tasks. This work represents a step forward in the ongoing effort to make language models more capable and reliable, particularly in complex problem-solving scenarios.